Hello friends, I'm Commander Atul Kumar Rohati sitting in front of you and talking to you. I'm going to speak on behalf of ISHRAE Institute of Excellence. As you are aware, we have started a talk series called HVAC Talks in which we are going to speak to you on various topics related to air conditioning and air conditioning. In, the, s- in that series, we have started a sub-series called Chill Water System, and it is the second talk in that series. Today we are going to talk about estimation of chill water system flow rate. If we know what is the cooling load on the cooling coil, how do we decide how much chill water is required to flow through it per unit time? If we know the total load on cooling coils, chill water flow rate can be estimated based on this relationship, which is Q, which is where Q is the total load is equal to M into Cp into delta T. Let me tell you that M here is the flow rate, mass flow rate, M into Cp into delta T, where Cp is the specific heat of water, and if we are talking in MKS units, then it is 4.18 kilojoule per kg per degree centigrade. And delta T is the temperature rise in chill water across the cooling coil. So if we know this, uh, that is the total load on the cooling coil Q. If we know Cp, which is a material constant, and if we know delta T, which is a design constant for the specific project that we are doing, then we can calculate the mass flow rate that is needed. What it is like? Normally, a chill water system operates between 6 degrees and 12 degrees centigrade. Please mark that I have said normally a chill water system operates between 6 and 12 degrees centigrade. There are chill water systems which work at a different in a different temperature range. But chill water system, the starting temperature cannot be much below 6 degrees centigrade. Maybe it can be become 5.5 or 5 degrees centigrade, but not below that. And chill water systems are also used for cooling uh, using radiant and convective technologies, where water is made to flow through tubes and air will come in contact with that and get cooled. But please remember that in all such conditions, there will be possibility of dew formation, and the temperature at which chill water is supplied to those systems is always below the dew, above the dew point of that particular room. So normally, an air conditioned compartment, a room, the dew point will be around 14 to 15 degrees centigrade, and therefore the chill water system supplies water at 16 degrees centigrade for such requirements. Why can't we have water at lower temperatures lower than 6 degrees centigrade? See, water density is maximum at around 4 degrees centigrade, and on cooling below this temperature, it starts expanding. There is also a possibility of freezing. A standard practice that the chiller manufacturers follow is to keep the lowest temperature, well above 4 degrees centigrade to avoid any freezing and consequent failure of the pipes in the evaporator. Now, knowing this, that the starting temperature is 6 degrees centigrade, supplying temperature is 6 degrees centigrade, return temperature is 12 degrees centigrade, we get delta T of 6 degrees centigrade. Now, if we are given that we have a system which is of 100 kilowatts, we have a cooling coil where the load is 100 kilowatts. Can we compute what is the amount of water flow required per unit time? Well, why not? We can. See, all that is required is that we have to understand that this relationship which is given in blue, Q is equal to M into Cp into delta T, where Cp is the specific heat of water, which is equivalent to 4.18 kilojoule per kg per degree centigrade. We can calculate the mass flow rate. M is equal to Q upon Cp delta T. And C for 100 kilowatt, we can compute that it is about 4 kg per second or 4 liters per second. So that is the water quantity, water flow rate that is required for a cooling coil, that is where the cooling load is 100 kilowatts. This calculation we have done in MKS system. In case if you are following FPS system, then what change will be there? Let's examine that also. The Q given here is 30 TR, 30 tons. Delta T is given as 11 degree Fahrenheit. It could be different, and we could compute that the chill water requirement for that particular requirement. Cp is 1 BTU per pound per degree Fahrenheit. That is the definition of BTU itself. That BTU is the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. Q is equal to m into Cp into delta T. The relationship, scientific relationship remains same, which is given in blue. We also know that 1 TR is equal to, that is ton of refrigeration, is equal to 12,000 BTU per hour. The density of water has been given as 62.3 pound per feet cube, and normally we get the flow of water in FPS in gallons, and we know 1 gallon is equal to 0.1337 feet cube. Now, using the same relationship which was earlier given in blue, we can have m is equal to q upon Cp into delta T, and here the Q is 30 TR, 30 TR into 12,000 BTU per hour. So in an hour it is 30 into 12,000 BTU divided by Cp of water, that is 1, and delta T being used is 11 degree Fahrenheit. So we can calculate that it is 32,727 pounds of water per hour. That is equivalent to 545 pounds per minute. Now this transforms to, because density is given, and the 1 gallon, how much it is in feet cube, that is also given. We can calculate that flow rate required is 8.75 feet cube per minute, or flow rate is 65 GPM. So this was about how we can estimate the water requirement for a chill water system. Typically, or a thumb rule calculation, people give design margins also. The consultants or the practical users, they say that for every TR it is around 2.5 GPM of water that is required. See, in those conditions, delta T could be different from 11, and they are also giving a design margin. Normally, design margin is a concept that we try to cater for the uncertainties and also degradation of the system in future. And for that, we keep certain amount of margins. So here it is coming 65 GPM. We could use 70 GPM or 75 GPM depending on our level of ignorance about the system and its performance. In my next talk on chill water system, we will discuss how do we estimate the pipe diameter. That depends on velocity of water, minimum diameter of pipes, and the role of velocity. So that's about it, about today's discussion, which was about estimation of amount of water flow required. If you want to know more about air conditioning, please do join ISHRAE Institute of Excellence and step into the world of HVAC. Our contact numbers are given here. Thank you for watching this video. I would request you to give questions or comments as to which is the next video that you would like to see, and we will try to make that and give to you. Thank you very much. Thanks a lot.